Okay, so higher order derivatives. So as self-explanatory as the name is, it's pretty obvious what they mean. We've talked about derivatives in a single variable right now. So if we have f of x, right, and that's equal to x squared plus 2x plus, I don't know, 1. We've tried to find the derivative, the first derivative of this, and we have succeeded in doing so. But what if we want to like move even beyond that? What if we want to calculate the double derivative? What does that turn out to give us, right? So we're going to use the same logic over here as well. We get a 2 over here because it's a 2x, right? The coefficient is going to be reproduced as the derivative, and this is going to give us a 0. What if we want to go beyond that? Well, if we try to do that, what do we get? We get a 0. And if we move on and on and on, it's still going to give us a 0 because it just approached a constant, and it will keep on doing that. So if we have fn to the power x, in this case where n is large, it's still going to give us something close to 0, right? But the idea is of higher order derivatives, we need to be able to express them in a simple form. I'm going to be using a general distance equation that you guys might have seen earlier. This is known as the distance equation. It changes with respect to time t. So the variable over here is t. So we have the initial distance, right, or displacement in this case, and we have the initial velocity times the time, right, for which the journey has passed, and we have half at squared, where a is the acceleration. So these are all constants, right? So v0 is a constant, initial velocity, right, and a is the acceleration that remains constant throughout the trip. So if we were to differentiate this with respect to time, like the first differential, we know that s0 is a constant, but t isn't, right? T is a variable. So if we differentiate it, we get a v0. Think of that as 2x, right? So the 2 is going to come as it is, and x is going to disappear, right? And if we try to do that for t squared, so remember what happens for x squared, the 2 just comes down and the power is subtracted by 1, right? So we get half times a, which is a constant, it's going to remain there, and this is going to give us 2t, right? And sorry, didn't mean to cut t. The 2 cancels out with the 2, and we get the first derivative as v0 plus at, right? And if you think about it, if we try to take the derivative again, what do we get? Well, the v0 would disappear in this case because that's a constant, right? You know that what that ends up as. And the other thing is that we get, when we differentiate this term, we get an a, because basically this is like x, right, or 2x. It's going to give us a 2, and this gives us a, which is the acceleration. So the idea is we moved from the displacement, right, towards the velocity, and that eventually gave us the acceleration, which is basically represented by what? An a. So it's kind of like a regular distance phenomena that you guys need to be familiar with. This might come in the section of related rates. So it's important to understand that if we try to differentiate any term, any equation that gives us the displacement, it gives us the velocity, and if we differentiate it again, the double derivative basically of the displacement gives us the acceleration, right? So differentiate the displacement, get the velocity, differentiate the velocity, get the acceleration. It's just a general rule that we can basically observe in this particular case as well. Another terminology that you guys should be familiar with is that if we need to represent derivatives in different forms, they just can be represented by the number of primes that are on top of them. So that's one way to represent it, and another way is basically just saying that what the number of times we're differentiating could be represented by a number in the brackets. So that's the first derivative, that's the 0th derivative, right, and that's the second, and this could go on and on to the nth derivative, right? So, and even if we were not to do that, we could write it as df by dx, right? Well, if it's a function f, so it would be just f, right? But df by dx is another option, and for the first derivative, and then we have d squared f by dx squared as the second, and then the cubed f by dx cubed, and this would go on and on. So like this is notation that you guys should be familiar with. It's a relatively easier concept, not something you'd have difficulty with at this point, but you know, it's just some terminology that you guys need to be aware of. Okay, so see you guys in the next video where we're going to be talking about implicit differentiation.